All right, so let's go back and find where we need to go. So let me pull up the list here. So where we left off last time was, I think, determining the number of input and output of arguments, right? I think that's where we were at, which was the, what was that function? It was like something in and out, narg in, narg out, something like that. But what we're going to do right now is we're going to pick up some of the more other important things we have to do. This isn't it. Let me get to it. So right here, this is where we're going to start. So this right here is, I think, something that might be useful and valuable for all of you. So really quickly, it says 6.2, this is creating your own toolbox of functions. So essentially what this section is, it tells you how to, so obviously MATLAB, whenever you create a file, it pulls from a specific file that you are working under, right? But for your toolbox, you can set another file that has all your functions in it. So if you want to create functions and then have them all in one file, this is one way to do that. So it says, when you call a function in MATLAB, the program first looks in the current folder to see if the function is defined. If it can't find the function listed there, it starts a predefined search path looking for a file with a function name. To view the path the program it takes, as it looks for files, select set path. So that is a little function you put in, or a little command, set path. And then it says from the home tool strip, type path tool. So essentially what this is that you are now going to be able to go in here, and you're supposed to be able to set the path that your that MATLAB looks to find your functions, okay? So this could be a folder that you put on your computer that says MATLAB functions, and you could have it look here. So let me see, it says the path tool allows you to change where MATLAB looks for functions. As you create more and more functions to use in your programming, you may wish to modify the path to look in the directory where you've stored your own personal tools. For example, suppose you have stored the degrees to radians and the radians to degrees example in a directory called my functions. You can add this directory to the folder path by selecting add folder from the list, and it says you'll be prompted to either supply the folder location or browse to find it. So if you go and find this folder, it will now use that folder to find it. So right here, this is what I think it does, although I could be wrong. I think what it does is it looks down all of these paths and finds it. But if you add your folder to it, it'll find it as well, right? So basically, if you want to put all of your functions in one place, if you ever need to, make a folder and then you have to add it to the path. Does that make sense? So you don't have to keep putting them in the working folder, right? You don't have to keep, moving them around. You can just have them in here in one folder, all your functions for your toolbox. So that was one thing that we need to cover. The next thing, this right here is part of your homework. Your last question, I think, has you create an anonymous function. If I'm mistaken, does anybody have it open in front of them? Fairly certain it does. So I think the last question that you do says you have to create an anonymous function. And so right here, this is the section on anonymous functions, so do pay attention here. So anonymous functions and function handles. So anonymous functions may be included in MATLAB programs with other commands, or may be defined from the command window. Normally, if you go to the trouble of creating a function, you'll want to store it for use in other programming projects. However, MATLAB includes a simpler kind of function called an anonymous function. Anonymous functions are defined in the command window or in a script, and are available, much as the variable names, only until the workspace is clear. To create an anonymous function, consider the following example. So essentially what an anonymous function is that you can define a function in your code using the anonymous function without having to save it previously and calling it up. So now you might be wondering, you're like, oh well, then why the hell do we do the other thing, right? Why do we save all these other functions, and whenever I can just do it during my initial window, right? Well, the reason is because once you're done with the question, this function doesn't save. It only exists inside of your workspace as you have the workspace open. So this is something you won't be able to call up unless you save it specifically. You will not be able to call it up in other files. So that's why. So this one is basically, think of it as like a one-time use, right? Sort of thing. You can use it in this command window, but once it is gone, it is gone. Alright, so let's look at this. So it says, to create an anonymous function, consider the following example. So right here we have ln, so everyone knows that's natural log. And it says ln is equal to @x space log x. Right here, just to show you the type what they're talking about, the @ symbol alerts MATLAB that the ln is a function. So having ln is equal to @x, essentially what it's saying is that this is a function, and specifically this is an anonymous function, right? And then it says immediately following the symbol, the input to the function is listed, which is x in this case, right? So @x means that this function will have an input of x, okay? And then it says finally the function is defined. So right here the function is log of x, right? So really quickly, let's go through these. It says name ln, so the name of the function ln, the value, so it's essentially right here is x log of x. Size, they're just showing you like this is like size of the actual file, but I don't really know why. And then right here size 1 and 1 to 1, so it's a 1 by 1 variable. Alright, and then the last one, I guess they give you a little hint here. It says think of function handle as a nickname for the function. So this is something that you're going to like know it by. So right here it says anonymous functions can be used like any other function. For example, the natural log of 10 gets you this number out, right? So they just typed in ln 10, right? Because we've defined it up here. And once you put in ln of 10, it's going to do this. Now, I know you guys are probably like, well, ln is something we already know, right? Correct. But you can define anything up here, right? You could have put @x, and you could have put a very, very long thing up here, whatever you might have thought of, and it would have done the same thing. So, and it says, once the workspace is clear, the anonymous function no longer exists. Anonymous functions can be saved as .mat files like other variables and can be stored with the load command. For example, to save the anonymous function ln, type save my_ln_function ln, right? A file named my_ln_function.mat is created, which contains the anonymous function ln function. Once the workspace is cleared, the function no longer exists, but it can be reloaded in the mat file. So really quickly, how this one works is that essentially how you've been pulling up those like thermocouple data, like those questions, it saves it like that. So essentially you'll pull it up, you'll do like load, you'll type in the word load like you have been for like the thermo scores and all those data, and you'll put in the name of the file and it will pull in that function now. And then it says it is possible to assign a function handle to any function. Earlier in this chapter, we created a function file called distance.m. So function result, I think this is something we did. I don't know if we did it, but earlier in the chapter, I think they have a practice question or something that has this in it. And so to change the function handle, the command says distance_handle is equal to @t distance t, right? And then it says by doing that, it assigned the handle distance_handle, which is what they put in here, to the distance function that we made earlier. Let me see if there's anything else that is super important in here. Oh, this one just tells you that you can find the number of inputs like you can with other functions. So just once again, this type of question is going to be on your homework. It is the last question. I'm fairly certain. I could pull it up, but I'm pretty sure. I'll actually do it anyway. I'll just pull it up. So right here it says create an anonymous function. So yes, create an anonymous function right here. So this is something that you'll have to do. And what that means is that you're just going to have to, in your code, define a function just like you did here. But they'll essentially give you the equation, right? It's MCP delta T for changing or energy, or it's energy change of water. So they give you the actual equation, and you just have to put it in a form of a anonymous function, right? Is that clear? Like what the expectation is for that question? All right. So then I'm going to go over a couple other ones, but some of these I'm not really sure about where we're going to use them, but I'll go over this because it's really quick, because as you can see, this is the end of the section. So we'll go over that. All right, so it says functions. So MATLAB's functions have an odd but descriptive name. They are functions that require other functions as an input. One example of a MATLAB built-in function is the function fplot. This requires two inputs, a function or a function handle, and a range over which to plot. We can determine the use of fplot with the function handle ln as defined, or demonstrate the use. So right here, this was what we just demonstrated, right? This was the anonymous function ln that we just created, right? And then down here, fplot, as they said, requires a function over and a range, right? So over here, we have fplot, ln, comma, and then they specified the range of values to put it over, right? So, as you guys can see, by doing that, it gives us a, I'm assuming a natural log plot. So, although I always forget what they actually look like, e to the x and all that, but I'm pretty sure that's what it is. So, essentially, you end up getting this, and the reason why, so this right here is that they, essentially what a function is that you can create a function that also requires an input of another function, right? Like I said, I didn't know really, yes, Blake, functions require other functions to function. So, like I said, I didn't really know where we would use something like this all that much. So I didn't really, think it was something too important to put into your homework. But essentially, just know this is that if you need a function that if you need to create a function that requires another function to be part of it, you can do that. It is a function essentially. And they gave you an example of a built-in one, which is fplot, right? And fplot requires it. So that's why I didn't really know where we'd use it, so I wanted to be a little less descriptive on this one. But then the last one I actually think is somewhat important, so we're going to go to it. It's kind of like, you remember subplot? It's sort of like subplots, but for functions. So I actually think this one's fairly useful. And it's got a little bit of stuff in here, but alright, so this is the last section. It's called subfunctions. So subfunctions can be created by grouping functions together in a single file. There are two approaches. You can add subfunctions to a script, or you can use multiple subfunctions in a primary function. Subfunctions can be used to modularize your code, and to make the primary code easier to read. They have the disadvantage that they are only available from the primary file and cannot be used by other programs. Alright. Here we go. Then it says using subfunctions in other functions. So it says each MATLAB has only one primary function. The name of the M file must be the same as the primary function name. Thus, the primary function stored in the M file, my function M, must be named my function. Subfunctions are added after the primary function and can have legitimate MATLAB variable name. Figure 611 shows a very simple example of a function that both adds and subtracts two vectors. The primary function named SumFunction demo. The file includes two subfunctions, add and subtract. So let's look at this really fast. So right here. So I don't know if you've seen this, but essentially this right here is the first function, right? Right? You guys can all see that. This is the first function. And it is named, function, subfunction, demo, xy, right? So it requires two inputs and, etc., right? Then they have another function down here, which is subfunction add, subfunction subtract. So what this is basically saying is that if you wanted to do all of your homework questions in one file, this is the way to do it. Essentially, is what it's saying, is that you can do them all in one file, and then you could call all your functions could be called in one homework, and you could get your answers just by doing this. So we'll demonstrate that in just a second, but let me zoom back out. Alright, so it says MATLAB allows the user to create subfunctions within a function M file. I'm tired of saying the word function. This file includes the primary function, subfunction demo, and two subfunctions add and subtract. Notice in the editing window that the contents of each function are identified with a gray bracket. So that would be like this right here. Essentially, it shows you that one's a parent of the other one, right? So if you hit this minus sign, it would kind of fold up, right? It says each code section can be either collapsed or expanded to make the contents easier to read by clicking on the plus or minus sign included with the bracket. MATLAB uses the term folding for this functionality. So it says example 6.5 demonstrates the use of a more complex example. So we'll go look at that in just a second. But it says, so we're going to walk through this one just kind of really quickly as we move down. But it does do some very long script here, but let me see what you're having to type here, Blake. Okay, so you're not typing anything, got it. So here's the problem, is that this right here is just a confusing example. I was gonna look at it, but I remember that the problem is that what they do is they say use this. So this is another criticism I would have, is that it says use this, and you're supposed to find the area under the curve using 3 or 4 different rules. So essentially, this right here is supposed to demonstrate using your the subfunction thing you're gonna have this one, this one, this one, and this one all within one function, right? And they say use this and use it at this range. Okay. Then it says down here to use an easier one. They say use an easier one. They're like, just use this one now instead. So do this, right? So it's to confirm whether you can do it by hand or not, which is fine, right? Like, no problem with that. Essentially, they're having you find the area under the curve of this. So like I said, I just want to make sure we're starting in the right place. So I want to start down here. So this is develop a hand example, which is usually how they do things. So right here, they find the area under the curve from 0 to 5 of this right here, because it's fairly easy. They want a result that you guys by yourselves can tell if you're on the right track based on if you get the answer by hand. This is a pretty easy one to do. So that's why they did it. And so they found it using one of the midpoint methods, I think. Or they just did average y values times the difference in x values. So there you go. All right. So right here, this is why I don't like this solution, is because they use if and else if, which is a more programming language that we haven't talked about yet. So really quickly, don't focus on that. Like this stuff right here, else if, don't focus on that. What we're going to look at is the subfunctions part, okay? So right here, it says function I. So this is integrate f xl xu in. This is the primary function, okay? So they've labeled all this. So, and they've put a help thing here. So if you did help, it would pull up what this is. So it says f is a function handle. XL is the lower limit of integration. XU is the upper limit of integration. And N is the number of segments to be used in the integration. Okay? And then it says N plus 1 is the number of data points remainder with remainder N2. So this is the remainder function. All right. So what they did is that if you look, this first one, essentially they wrote some code, whereas like if n equals 1, n equals 3, all this stuff. But that's not what we're really looking at. So think of it this way. This is the first function, right? Okay? This is the first function. Then, right here, this is the next subfunction. This is the first subfunction within that one, okay? And so, it says function output. So we write this function just like other ones, right? Function output is equal to trap f. So this is the trapezoid method that I think that they're doing here. I'm assuming from trap f. So trapezoid method, they have f, xl, xu, and n. So really quickly, they do so x is equal to linspace. I think this is that space command that I don't know, you'd have to look at it back chapters. I don't remember exactly what it does, but I think it's something, I think it's line spacing. And then right here, you have y is equal to f of x. And then they define h as xu xl divided by n. So remember, this is the trapezoidal method of finding area under the curve. And then you have total is equal to 2 times the sum of y minus y of 1 minus y of n, right? So essentially they're using all these end in terms, but essentially this is what I want you to know is that right here, this is the second subfunction, or the first subfunction, the second function though. And so right in this area, this is how, so essentially you have one great function up here. This is the big one at the very top, right? And then the subfunction under it is the trapezoidal method. And then right here is Simpson's 38 rule. And then this is the Simpson's 13 rule, right? Which they've described as methods of finding area under the curve. So within one function of integration here, how did they designate it as a subfunction? So essentially, it's just working under the parent function. So essentially, it's a function within. So really quickly, they saved this function as the primary, because remember in MATLAB files when you save the function, it has to have the same name as the function you created as. So this function is up here, right? But this one just kind of is tagging along. All of these other ones are kind of tagging along inside of it. And so I'll go back and read that section again. So it says each MATLAB function has one primary function. The name of the M file must be the same as the primary function name. Thus, the primary function stored in any M file must be named myFunction. So for myFunction M must be named myFunction. Subfunctions are added after the primary function and can have any legitimate variable name. So, like I said right here, they have, this is the primary, right? And it says this function both adds and subtracts the elements stored in two arrays. So it's addition result, add xy, subtraction result, add xy. Then they have a subfunction that all it does is add, and then they have another one that all it does is subtract, right? So this right here is these are the subfunctions. And like I said, like they said, it can have any variable name, just like normal file, essentially. It has no, it's just additional functions tagged into the main one up here. That's all. Well, so the reason why they're called subfunctions, I don't think it's like a classification like you're thinking. I think it's subfunctions are just any function that is not the primary. I don't think it's any. I don't think the program classifies it. Like for example, if you wrote this like really quick, you see that this is function, right? It looks the exact same. It has this bracket and everything. But the primary function, the one that your file is going to get called. So when you try to call this file right here, you don't call it by this right here. You will call it by its name up the one the primary, and these are just tag-alongs, right? They come with it in variable names essentially. But this example I don't like because they have a bunch of like programming language and it's not something that we should have had to see yet. But okay. So essentially this right here, so let me go back through it one more time. So right here, this is the primary, right? The primary function is all of this up here. So just forget all this stuff in the middle though. All this like all this stuff about like else if and all that. Just forget about that. And then down here we have the first one. This is the first subfunction that is contained within the primary. And this one is just using, it looks like it's doing the trapezoid, right? So because they've defined it right here, remember to define functions, you do function output and you name the function. So trap_f is going to require an input of f, xl, xu, and n, right? And then down here, next one, another one. So function output, you have Simpson's 38 rule, which is f, xl, xu. And then the last one, Simpson's 13m, which I guess that's this other one. I don't even remember. Honestly, I don't remember doing any of those. I did like a bunch of other different ones. I do remember the trapezoid one. And then you put in f, xl, xu, and n for the third one. And so, really, really fast, they have you test it here. And so what you do is they call the function, they do... so it says test solution. Test the function with a simple equation of a straight line values from n from 1 to 5, which is what they did here, right? And so, I think they put in... it looks like they put in coordinates. So essentially what it's saying is that, so real quick, we have to remember what these are. So they're not coordinates, but they're just x and y values. So integrate f, right? And f is right here. So this is the function, remember that. So they made this function right here. This is a anonymous function. And the reason why it's an anonymous function is because they @x'd it and they put in the function here. And the reason why they did that was so they could change this more readily. And so essentially if they need to change this function, they can just change it and it will do the exact same thing with all of these. So they did an anonymous function here. But this is what we're going to read this. So it's going to integrate f, which is this right here, from a range of 0 to 5, starting at 1, then go down to 2, then 3, then 4, then 5. So it's going to do with n equals 1 to 5, and it's going to be start at 0 and go to 5. So it's going to look, I don't think, so yeah, x equals, so the limits of integration. They defined the limits of integration from 0 to 5. That's essentially what they're doing. And so if you do that, this is what you end up getting. You integrate, and you get all of these. And so essentially what these methods do, though, is that the more you... so these are... I don't know if anyone's taken numerical methods yet. Maybe someone in here has. Essentially, they're approximations of area under the curve is more or less what they are. So obviously, I think you guys all know is that integrals are area under the curve. They're obviously inverse derivatives, but they are area under the curve. That is what they represent. So if you did the integral of this, your answer would be this. It would be all this area shaded. But what these other methods do is, like these Simpson's 38 and this trapezoidal rule and all that stuff, it helps you, it can approximate the area under the curve using these shapes. That's what those do. I don't know if you guys have taken numerical methods yet. Have you? Anyone in here? It's probably not on your scope quite yet. I don't remember what it's called and what class number it is. Okay. But yeah, essentially, you use trapezoids. So really, I guess this is the better way to describe it is essentially under this curve, you're putting a n amount of trapezoids under this curve, and it's using that to approximate the area, more or less. So that's the and there's other ways too. There's like rectangular. There's midpoint. What's another one? There's like a bunch of popular ones, but you usually learn those before you learn integrals. You usually learn the numerical ways of doing it because integrals are a little more complex generally, but some of these can get complex. Like numerical methods was a fairly complex class. Didn't like it too much. So, right here, let me see if so this is for you though. So 6.52 subfunctions in MATLAB programs. When could you use it effectively in a script? Imagine that your instructor, I know we're breaking the fourth wall here, that your instructor has assigned 3 homework problems, each requiring you to create and test a function. Problem 1, create and test a function called square to square values of x. Assume x varies from -3 to 3. Create and test a function called cold work to find the percent cold work experienced by a metallic rod as it is drawn into wire. Cold work is described by this equation. Problem 3, create and test a function called potential energy to determine the potential energy change of a given mass. Right here. Your function should have 3 inputs, m, g, and delta z. So they've just given you 3 questions, right? To complete the assignment, you would need to create 4 files, 1 for each function and 1 to call and test the function. So that's the normal way, right? You would have to create 3 function files, and then you would have 1 actual turn-in file, where this is the one that would show all your answers, right, as you called them. So it says you can use subfunctions to reduce the number of files to 1, right here. So, function 1, sample homework. So that's what they've named it, and this is essentially the solution. So right here, they commented problem 1. So problem 1, they have x -3 to 3. Disp. Maybe I'm missing that, but what do they call it? I'm confused why they named it disp though. Why is it that? Is that just a function? Display? I think it's display. Yeah. Yeah, I'm pretty sure it's just display. Yeah, okay. So essentially it's just gonna show you these things right here. Yeah. No, I didn't do Python. I did C++. Mine was, I think, QN, I think is what it was called for C++. But yeah, display. Or QOut. QOut is what you used to say. But anyway, essentially it would display problem 1, and it says display the squares of the input variables are listed below. So essentially you create your function y equals the square of x, display y, right? And so right here they solve the first question in 1 file. Down here they do the exact same thing. They solve it in another file, or in the same file. That's what I meant. So problem 1 is solved here. Problem 2 is solved here. Problem 3 is solved here. And then at the very end, essentially they're putting in all of their, so real quick, they're putting in all of their values right here in this first one, right? And then in the final one, they're creating the 3 subfunctions that solve each one of them. So right here, function result equals square of x, result equals x squared, essentially, right? And then down here, function result, cold work, R1, RF, which is things that they give you in the question. Results, they typed in their equation there, just like you would in doing other functions. And then they did another one right here for the potential energy. And then they ended it. So essentially, if you did this file right here, this is the code, or this is all of the functions required to solve every single one of the questions they gave up here. So now if you went and tested it into an actual file, you would get your answers essentially. So you could do them all in one, is what subfunctions are. Now, just for anyone in here, you don't have to use this. You know, if you don't feel comfortable, like for example, I have a tendency to do things the long way because it's always the safe option to where I won't mess it up. Essentially, that's all how I always look at it, is that it's always the safe option. I won't mess it up. I'll create 4 files. So I'm going to demonstrate. I have a couple questions I picked out, and we have 13 minutes, so I'm actually going to pull them up really fast, and we're going to do them. I'll stay after if you want to look at this and see how to do something like this. But I have a couple questions I'm going to pull up now, and these are going to be ones from the first chapter, not first chapter, the first section. It's going to be from single variable input, double variable input, and then I think an anonymous function question. Those are the 3 that I think I looked at. So let's go back here. I don't know if this is the one I was looking at or not. This is the one that I've already done. But essentially, I was going to do these really quick. So let me pull up in MATLAB, which I already have it here. These are fairly straightforward, but alright, so these are, like I said, very easy, but I think it's worth it to look at it. So right here it says create MATLAB functions to evaluate the following mathematical functions. So essentially we have to create a function that does these, right? And I know you guys are probably like, oh, well, this is stuff you could do normally, right? You don't need a function to do that. I agree, you don't. But it's still something that obviously if it works now, it can work to other things later. So function output, which I think I gotta make sure I remember the syntax and everything. So really quick, it is function output, and then I think you have to name it, which I think is, I don't know, I'm gonna do a square function. Square function x, I think is what it is, and then output is equal to I guess you would just do x squared, right? So right here, I'm going to go ahead and save this. So this is what you have to do. So you have to save it. And so this is in a MATLAB. So I'm going to call it, remember, I called the function square function, so it's going to save as the square function. So now I have that right here. And then if I call this, so if I do, I don't know, let's do square. Wait, I'll make sure I did the variable name right. Yeah, square underscore x function. And let's say 4, right? Let's see if this works. And I have to save this one too. Another annoying thing about MATLAB. When x. So right here, as you guys can see, the answer has come up as 16 because I put a square function 4 into it. So 4 squared is 16. So I've called this function from using it right here. So square underscore function x, square underscore function, and then I put my value in there, right? Does that make sense? And now I'll do the next one really fast, but you'll get I'm not going to do all of these, but I'm just showing you that this is how you essentially are going to create your functions for like question 1. Question 1, they give you the actual function you're going to use, and you just have to turn it into this, essentially. So once again, function output is equal to, is this an inverse exponential? Like, is that what that's not, I guess it would be, isn't it? What would you guys call e to the 1/2 x? I don't even remember what it's called. It's been a long time, guys. What do you call that? Is it inverse exponential or something? Yeah, I have no idea. So I'm just going to call it e underscore inverse. I don't know. What do you call that? I don't actually, wait a minute. I'm pretty sure you don't have to do that. Oh, yeah, you do. Okay. And then you have outputs is equal to, and then you do exp to the 1/2 x. I'm pretty sure that's it. And then you have to say this again because there's E inverse, than what I named it. Is it normal exponential function? Yeah, I guess you're right, because essentially all this is a number. 1/2 x is a number. It just goes to 0. I guess that's right. It's a normal exponential. I guess whenever I think of normal exponentials, I think of it as to a number that is, greater than 1. But you're right. It's a normal exponential function. All right, so then this is E inverse. So I'm calling it again of, I don't know. So just to test it, you put in 1 here, right? Because then you'll know, inverse. There it is. So E inverse of 1, just to test this, you'll get E to the first. And that'll be something that we all know the answer to, right? Which is 2.718, which is what E is. E is equivalent to that. So this right here, these are your 2 function files, and I tested them right here in this one. All right. So then I will make another one here. So basically, this is how you do all of your your functions. Essentially, you'll create them inside of here. You'll save them, and then you'll make a new file and test them. So for your homework, because I put more emphasis on plotting rather than the functions, you're only going to have to do, I think, 1 function for this one. So for your first homework question, I think, let me pull it up again because I forgot exactly. So right here, you're going to have to create a function, which they give you the function, which is E equals mc squared. And it says use your function. So yeah, you're only going to have to create 1 function, but it's an engineering function essentially, or physics function. You're going to have to program that in, and then you have to use some things like semilog to plot it, right? So a lot of plots, plot heavy on this homework. And then the second question only requires you to do an anonymous function, so you're not going to have to make too many of these. So, but just know that this is how you do them. You create a file, create a function, and then you make a new little workspace here, an editor window, and you just test it like I did here. And now I'm going to do one with multiple inputs. So I think this is the one I did. No, this isn't it. It's this one. It was the grain size one right here. No, this is the Hall-Petch equation. I remember this. So this is... So it says materials composed of small crystals are stronger than metals composed of a few larger crystals. The metal yield strength, amount of stress at which metal starts to permanently deform, is related to the average grain diameter by the Hall-Petch equation, which is this right here. So sigma is equal to sigma naught plus kd to the negative 1/2. Okay? Where symbols sigma naught and k represent constants that are different for every metal. So they've listed it right here, right? So what I'm going to do is I'm going to do this one in here as well. So once again, script, there it is. So this one's going to be called the Hall-Petch equation. So I'm going to do function outputs Hall underscore Petch. Is it patch or petch? Petch, there it is. Hall-Petch, and then you do x. So really quickly, you can create actual variables in there. Like for example, there is a way to do sigma, k, and so sigma and I think sigma for sure, but k and d. D is obviously just d. But there's a way to do it and have them written into your thing. But we haven't learned that yet. So what I did is I just called them x, y, and z, right? And then what I did was, to help myself, is that I did x is equal to k. Then I did y is equal to sigma naught. And you could write these in there, right? Like you could write sigma naught as a very big, you could just write this. You could just say sigma naught. But there is a way to get the actual variable, little tiny symbol to show up. We just haven't learned yet. And frankly, I've never done it. So I usually write it like this, but I always, if I'm going to do it, I like X, Y's, and Z's. I'm a simple man. So I do, just for a help window, if I need to see it, you can do help, remember help hall patch, and it'll show you this. So X is equal to K, Y is equal to sigma naught, and D is equal to grain diameter, right? Like I said, I'm not telling you the best way to do it. Not really. This is just the way that it makes sense to me. All right, so then we have, what is it? Output is what comes next, right? Yeah, output. Oh, you're right. Z, thank you. Z is equal to grain diameter. Sure. And then we have outputs is equal to, and then you write your equation in here, right? So the equation, the Hall Petch equation is what is it? Oh, here it is. So it's sigma naught. So it's y plus, where is it? K is x, so x. And this is dot multiply, I'm pretty sure. Because I think they're doing it for a total, a range of values from 0.1 to 10 millimeters. So I think it's a dot multiply. And then it's times z to the negative 0.5, I think is what you have to do here. Ah, come on. Alright, so I think that is it. I don't know if I see anything that's horribly wrong with it. We'll see here in a second when it doesn't like it. So I gotta save this. I have a tendency to mess very simple things like that up. So let's see if I can do this. So let's do Hall underscore Petch, and then we have to put in our numbers. So the numbers right here. So the first one was X, and if I go back over here, I put X is equal to K. So the first one is 9600, so 9600. The second one was 1200. And then the third one, I'm going to do grain underscore diameter. And I'm going to set the range up, so I should enter down here. Diameter is equal to 0.1. I don't know, what should we have this go up by? I'll just have it go up by 1, I guess, to 10. I don't know, like it could just be a big one and just do that, but whatever. So let's see if that works. It might not, but we'll see. Okay, yeah, if you guys have to go, if you have a test, you should go. Like, someone just said they have a test, so if you gotta go, man. Let me see this. Grain diameter. Oh, it only has it as 1. Oh, I didn't hit the other semicolon. That's why. I was wondering. Ooh, didn't like that. Oh, yep, now I remember. Let's see if that does it. Yep. Yep. So right here, I'll pull this up. So obviously, because I did 0.1 going up by 0.1 to 10, there's a lot of things here. Yeah, I missed out on hitting a colon. But essentially, this is how it looks. So for every 0.1, it moves up this. This is what it is. And so, once again, I called this one similar to the other ones. And like I said, you guys can set this up however you wish. I just, like I said, X, Y, and Z made sense to me. But it doesn't really matter as long as you know what to put in here, right? As long as you know what to put in here, it's fine. And you get the same result. And so you get this. These are the outputs.